All right, watch and listen carefully here, guys. These are probably the hardest 10 naming ones that I've put together in a while. All right, but I mean, we've been doing naming now for like 2 weeks, so it's time to be good at this. All right, it's time to be able to do the hard ones. First one, I've got a metal, sodium, with a polyatomic ion, carbonate, so it's an ionic compound, so I name it as such. This is sodium carbonate. No capital letters. If it has capital letters, it is wrong. Okay. Number 2, I've got iron with sulfur. Iron's a metal, so it's an ionic compound. Iron is also a special metal. It has 2 possible charges. Sulfur is always -2. That means this is the iron that is +2. So this is iron, Roman numeral 2, sulfide. For number 3, 2 nonmetals, so I got to put prefixes in. I've got triphosphorus. Okay, penta. That's not a capital P. That's a small p. Pentabromide. Okay. And number 4, I've got copper, which is a metal with the polyatomic ion, so this is ionic. Copper is also a special metal, and it can be +1 or +2. Okay, sulfate is always -2 according to your table. That means this copper must be 2. All right, so this is copper, Roman numeral 2, sulfate. Okay, incidentally, that was one of the unknowns that you used in your lab yesterday. Okay. All right, and CH4, both nonmetals. Okay, this is carbon tetrahydride. How do I know hydrogen is acting as a nonmetal? It's listed second, or anything other than first. Okay, it's behaving as a nonmetal. Anyone know what the common name for CH4 is? Methane, yeah. Okay, that's fart gas. All right. Okay, questions on any of the first 5? All right. For number 6, I've got dinitrogen. Okay, hexachloride, so it's obviously molecular with all the prefixes. All I have to do is put in the right numbers. Nitrogen, 2 of them. Chlorine, 6 of them. Okay, do I reduce molecular compounds? No, only ionic. And that's specifically why I did that, to see if people remembered that rule. Okay, I know that probably seems cheap, but it's one of the things I got to know. All right, number 7, I've got cobalt 2 fluoride. The 2 tells me to use the charge +2. Not that there are 2 cobalts, there might be, but there aren't. Okay, in this case, okay, I need to use the 2+ charge. So cobalt, okay, whoa, I'm writing it again. Why am I doing that? Okay, CO, 2+, fluoride, 1-, COF2. All right, that's our formula. Okay, ammonium phosphide. NH4 is ammonium. Okay, it's the only positively charged. Okay, polyatomic ion on your chart. Okay, and phosphide. Okay, that's just P, and it's -3. So if I'm going to do the drop and swap, the P stays as a 1. What do I have to do with this 3? Put it in bracket. Right. Okay, I put brackets around the NH4. I put the 3 outside of the brackets. NH4, 3P. Okay, calcium nitrate. Okay, calcium's a metal, so we're swapping and dropping again. It's 2+. Nitrate is NO3, and it's a -1. So when I drop and swap, I need brackets again. And the 2 goes outside of the brackets. All right, and last one. It basically employs every single rule possible for an ionic compound. Okay, it's got a Roman numeral, it's got a polyatomic ion, it's going to need brackets. Okay, all that kind of stuff. So lead is Pb, and it's 2+. Permanganate is KMnO4, and it is -1. So when I drop and swap, I need brackets here and a 2 there. I don't know that that compound actually exists, but oh, sorry, there's no K in there. Just MnO4. Sorry, guys. Nah, yeah, it's not lead potassium permanganate, it's lead permanganate. MnO4. 2. Sorry about that. Okay, so give him a mark out of 10. Let him see it. Once you've seen yours, please come put it in the box. All right. Sadie, can I have you just turn off that front bank of lights? Thank you. All right, so solubility and properties of water. All right, it seems like, you know, when there's a rule about matter or a rule about chemistry, it seems like water is always the thing that is the exception to the rule. Okay, and there's a reason for that. We're going to go over that today. Water is a special kind of compound. All right, and as a result, it behaves differently than a lot of sort of standard type things. All right. Of course, water is obviously very important to us. Okay, without it, there would be no life on Earth. So, okay, it's important actually that some of these properties are present, some of these strange behaviors, because they make life possible. All right, we'll go over what those are. All right, so we're going to look at terminology related to solubility. Okay, solubility is what? What he said? Okay, yeah. So the ability of something to dissolve in water is solubility, okay? Or, not always water either, okay? The ability of anything to dissolve in something else, all right? And so we're going to look at terminology like solvent and solute, okay? Solute's the thing that gets dissolved. Solvent is the thing that does the dissolving, all right? That's why we often call cleaners solvents, all right? If you get oil-based paint on your skin, does that wash off with soap and water? It does not, because oil-based paint has oil in it, and oil is not soluble in water. That's the reason we use it, okay, is because it repels water. If you paint your deck with oil-based stain, okay, the water hits it and beads up and runs off and doesn't penetrate and rot the wood. All right, that's the whole reason for that. Okay? It's a good application of solubility. Unfortunately, if you get it on your hands, it's hard to get off unless you use something that oil is soluble in, right? Like Varsol, turpentine, any other kind of paint thinner, if you're really brave, gasoline, okay? That kind of stuff will all take oil-based paints off. Why? Because oil-based paint is soluble in those solvents, right? Where it isn't in water. All right, everybody follow me there? Okay, we want to understand what is meant by the term polar molecule. And this term is going to come up time and time again, not just in this unit, but also in the biology unit. All right, because the fact that water is a polar molecule is related to how living things are able to use it. Okay, and lastly, understand because it is a polar molecule, water has many important and unique properties that make life on Earth possible. Must have just missed it. I see everyone. All the other ones I'm looking at have it. I don't know. Your printer must have just missed a couple. You can get it on your phone. Okay. So, some substances dissolve easily and others do not. Okay? And the degree to which they dissolve is solubility. Okay? So, we're going to look at, it says here chart in your text, but actually your chart is on the back of your periodic table. Okay? You have a solubility chart on the back of your periodic table, which we'll look at in a minute. Okay? A substance is said to be insoluble, okay, if it will not dissolve. So, insoluble means it will not dissolve in another substance. Okay? If a substance remains insoluble in a solid form, okay, we call it a precipitate. Okay, so if something is insoluble in a solid form, we call it a precipitate. Right, especially if it is formed in a chemical reaction. All right, and when we do our chemical reactions lab next week sometime, you'll have a couple of chemical reactions where you will mix two clear solutions together, and as soon as they hit each other, a solid will form. Okay? A solid will form, and you will see it as kind of a fine powder that falls out of the solution and collects on the bottom, hence the name precipitate. It falls out of the solution and collects on the bottom just like rain falls out of the sky. All right? That's where we get the name from. Everyone follow me there. All right, so here's our terminology. Okay, precipitate is something that is insoluble, and won't go into solution. Okay, Insoluble means it won't dissolve. All right? So you can kind of see here, this would be something that is soluble because we can only see one part. Okay? Whereas this stuff here has probably just formed, this kind of whitish blue stuff has just formed and is slowly precipitating, okay, towards the bottom of the tube, okay, where it will collect on the bottom. Okay? Can you get a precipitate of something that is soluble? Yes, you can. If you saturate the solution when you're making Kool-Aid, okay, if you continue to add sugar, right, eventually you will saturate the solution so that it can no longer dissolve any more sugar, and then sugar will begin to collect on the bottom. Okay? It's not a true precipitate, it's just that you've added too much. All right? Sugar is certainly soluble in water, right? But you've added a lot of it to it, okay? And now it will collect on the bottom. Is there a way to get that stuff to dissolve? Are there things you can do to increase solubility? You can heat the water. Solubility is affected by temperature. Okay? The warmer something is, generally, the more stuff it can dissolve. Pardon me? Yes, you can change the pressure. Okay? Pressure also affects solubility. You can stir it. Agitation will increase solubility a slight amount. Okay? Or at least it will suspend the stuff, you know, upwards where it hasn't had time to settle yet. Okay? Those, you know, it's not truly soluble, but it will cause a little bit more solubility to happen simply because you've changed how much movement there is of all the particles involved. All right? So those are things we can do to increase solubility. All right. Terminology. A solution, okay, is any mixture containing a solute dissolved, okay, in a solvent. Right? It is also known as a homogeneous or homogeneous, however you want to pronounce it, mixture. What does homogeneous mean or homogeneous mean? Right. You can only, there's only one visible part. All right? Everything has become one. All right? There's only one part. Okay? If something is heterogeneous, then there are more than one visible part. Right? Okay? Something's not dissolved. Maybe many things are not dissolved. You can actually set up things where you get several, okay, layers of things based on their density, okay, that don't dissolve in each other, and they separate, and you get a heterogeneous mixture. If you, it doesn't have to even be in fluids. Okay, if you go to Subway and you ask for salt and pepper, they have it in the same shaker. All right, is the salt dissolved in the pepper? No, it's a mechanical mixture. It's a heterogeneous mixture. They're both in there, okay, but they're not mixed. Okay, they're not dissolved in one another. They're mixed, but they're not dissolved in one another. All right, oil and water, okay, iron filings and sand, okay, things like that. Can you pull apart a mechanical mixture or a heterogeneous mixture? You can. Based on some physical property, okay, you can pull those things apart. If I had iron filings and sand, I could separate them with what? With a magnet, right? I just stick a magnet into the mixture and start swirling it around. Pretty soon I'd have a whole bunch of iron stuck to the magnet, okay, and I'd have sand left over. All right. If I had oil and water, okay, I'd just leave them sit, and eventually they would separate. Okay, their densities would cause them to separate, and then I could pull them off that way. Or I could heat it up until all the water boiled off, and then I'd be left with the oil. Okay, that wouldn't be a really good way to do it because you'd probably burn the oil all over the place. But all right, those are ways you can always separate a mechanical mixture based on the physical properties of the two things involved. All right, they've got something that's different. If I had, again, that salt and pepper mixture, all right, how could I separate those? Dump it in water. Salt's soluble in water, pepper isn't. Okay, so the pepper would float, okay, and not mix in. The salt would dissolve. They'd be separated. Then I could just pour it through a filter, okay, and all the pepper would catch in a paper filter, like a coffee filter, okay, something like that. There's always a way, okay, to do that. All right, if I get something to dissolve in something else, can I still separate them? Yeah, but not with a filter. Okay, like I can't take salt water, pour it through a filter, and have it catch the salt. Right? That's not going to happen. All right, the salt's going to go right through. It's dissolved in the water. But could I boil the water off? Yeah, then I'd be left with the salt. Okay, things like that, right? That's how distillation works. All right, so obviously, guys, okay, the way to remember this, okay, has to go with the prefixes, right? Okay, hetero means many, okay, and homo means one, okay? And that's the way you can remember it, all right? Okay. All right, solutes, okay, so terminology again. Solute is the substance that is being dissolved. All right, so salt in water, salt's the solute, okay? If you're making hot chocolate with the powder is the solute, okay? Water or milk, whatever you're dissolving it in, okay, is the solvent. Okay, so solvents are any substance that will dissolve something else. Water is often called the what? Universal solvent, okay? Because most things dissolve in water, at least to some extent, okay? Mr. Clean is a solvent, okay? So are any cleaners, okay? If you got Lysol or whatever, any of those cleaners are solvents because they help water to dissolve things that are otherwise not very soluble in it, like the lime stuff that kind of forms on the inside of your shower, the hard water scales and soap scum and stuff like that, okay? That stuff doesn't dissolve in water very well, right? If you've ever tried to clean your shower with just water, you probably wouldn't try that because it doesn't work very well, okay? But if you spray it with something else, with Tilex or like CLR or something like that, it comes off real fast, okay? Because those things are things that can dissolve, okay? These things that don't dissolve in water by itself, all right? Everyone with me there? Okay. Now, we said a precipitate, okay, is any solid which is produced in a reaction and will not dissolve in solution. All right, so it's produced in a reaction and won't dissolve in the solution. That's the important part, okay? Produced in a reaction, okay, and will not dissolve. Okay, now hopefully this link is going to work, okay, and I'll show you what that actually looks like here real quick. And it's not going to work. All right. Oh, that one. Okay, you can see in this picture here, guys, that we've got, okay, that the precipitate is actually, you can see it falling in kind of little clouds here, okay, out of the, from the top and down towards the bottom. All right, so that's kind of what we're looking at there. All right. Okay, sorry, that movie didn't work. Okay, now, things that are soluble in water that you might not imagine. Twinkies. How many people like Twinkies? Good, then this isn't going to ruin anyone's life. Okay. Well, they're not 100% sugar, but they certainly are not the original Twinkie. Okay, the Twinkie you buy in the store is no longer what it once was. Twinkies used to be cake with this filling inside. They're still technically cake, but they're not all natural, okay, as many things aren't anymore, of course, in the food industry. Okay, the original Twinkie contained things like oil and eggs and flour and sugar and stuff like that, kind of natural ingredients that you would use to make a cake. Okay, but when you make cake that way, cake doesn't last very long because bacteria and mold and stuff like that can grow on that kind of stuff. Obviously, people who sell Twinkies want them to be able to stay on the shelf if they don't sell in the first 5 days that they're baked. Okay, there's transportation time and stuff like that. So they started replacing a lot of the natural ingredients with artificial substitutes. Okay, here's the problem with doing that. When you replace eggs, okay, with artificial things, you lose one of the key physical properties of eggs: color. Twinkies are yellow because they used to contain eggs, which were yellow. When they are not made with eggs and made with artificial substitutes, they have the color of wallpaper paste or drywall cement and stuff like that. They're gray. They don't look terribly appetizing. So what do they add to them? Yeah, specifically, yellow dye number 5. Yellow dye number 5 is a known carcinogen and is banned in all of Europe and most other countries of the world except Canada and the United States, where we like Twinkies and we'll eat it anyway. Okay? There's also preservatives, obviously placed in Twinkies so they don't spoil on the shelf. Okay, a Twinkie has a shelf life of a couple of years in its package because it contains stuff that keeps mold from growing. Essentially the same stuff that they use in mortician's fluid. What do you use mortician's fluid for? Yeah, keeping dead bodies from smelling until the funeral. Okay, it's what they essentially pump into them, okay, that keeps bacteria and mold from growing on a corpse. Okay, well, these same things keep bacteria and mold from growing on basically anything. Okay, now they're in small amounts that the Food and Drug Administration says is okay and safe. So, you know, if the Food and Drug Administration says it's safe to eat, we have to believe what they say and we can eat them. Okay, but know that the original Twinkie, if you put it in water, okay, wouldn't dissolve because it had oil in it, and oil doesn't dissolve in water. Eggs don't dissolve in water, okay, things like that. Those natural ingredients didn't do that. The modern Twinkie, put it in water, and in a matter of minutes, you will have a solution of Twinkie. If you ever break your jaw, you can still have Twinkies, even if your jaw is wired shut, because you can put them in water and drink them with a straw. Okay? Something that is soluble in water that probably shouldn't be. Twinkies. There you go. Okay. All right. Solubility. Okay. Definition of solubility strictly is the degree to which a substance will dissolve in something else. All right. So how much solute can go into solution before the solvent becomes saturated. Okay. If something is saturated, it can't hold any more. All right. Now, that can be affected by the properties of the substance, okay, as well as temperature. We talked about that. You could stir it, you could heat it up, you could change the pressure. All of those things can change how much of something dissolves in something else. All right, solubility chart. This is on the back of your periodic table, so why don't you take that out right now. And we'll explain how to use it. Okay, so what you'll be asked to do at some point is that oh, sorry, it won't be on the back of those ones. You'll need the small ones if you don't have your own. Okay. Yeah, there you go. Yep. Okay, so what you'll be asked to do is, if later on when we start doing chemical reactions, you'll be asked to find out if any of the products are soluble, okay, or if any of them are precipitates. Okay. Basically, it means if I give you a compound, you need to be able to tell me if it's soluble or not, okay? And this is going to be only of ionic compounds because we know, of course, that molecular compounds are generally not very soluble in water anyway. All right, so let's say I give you this compound here, NH4CO3. Oh, I did that wrong. Put the brackets in the wrong place. Okay. NH4CO3, and there should be a 2 here. All right, so ammonium carbonate. I want to find out if that stuff is soluble or not. So what I do is across the top, okay, they've got the negatively charged ions, except in this column here. Okay, but they got most of the negatively charged ions. So what I do is I look for carbonate, which is right here. All right, and then I go down and look at these other 2 rows. Okay, you can see that the first row is very soluble. All right, so anything that's, if what's with carbonate is in this row, that substance is soluble. If what's with carbonate is in this row, then it is not soluble. Okay, they say slightly. We're going to change that to say not soluble. Okay, so looking at this then, I see that when carbonate is with ammonium, it is very soluble. All right, as are most ammonium-containing compounds. Okay, most compounds that contain ammonium are soluble in water. Okay, everybody follow me there? Okay, see how that kind of works? So if we always look for the negative compound, match it up with, if it's in the first row, it's soluble. If it's in the second row, it's not. So what I'm going to do is I'm going to list about 5 compounds here, and I want you to write next to them S or I. Okay, soluble or insoluble. Okay, so let's try. I'll give you a couple minutes on those ones, and then we'll do them together here. On this chart, are there going to be times you don't see the metal listed specifically? Like in the first one, with lead and sulfide. Okay, so if I look at lead sulfide here, okay, I see here's sulfide. It's soluble with hydrogen, sodium, potassium, ammonium, lithium, magnesium, and calcium. And then under here it says it is not soluble with most things. Well, since lead's not listed here, lead is with most. Okay, so is this compound soluble or not? It is not soluble. So this is insoluble. We would put an I, okay, beside that one. Everyone follow how that works? Okay, give you a couple more minutes on the rest. Okay, so let's go through these ones here. So for number 2, I've got calcium with hydroxide. Which one of those is negative? Calcium or hydroxide? Hydroxide. All right, so I go up to the top row here, okay, and I find hydroxides right down here on the end. Okay, says it is soluble with all of these things here, and calcium is in that row. All right, so this stuff here is soluble in water. All right, for number 3, I've got copper with chlorine. Okay, chlorine is the negatively charged one, and it's located right here. All right, says it is soluble with most things. If you see most in the soluble row, should you still look in the bottom row? Yes, especially in this case, since copper is the first thing listed as one of the things it is not soluble with. Okay, so this compound is insoluble. All right, for number 4, okay, we've got lithium fluoride. So fluoride is right here. Okay, it's soluble with most things, but not with lithium. So that one is insoluble as well. Okay, and the last one, sodium sulfate. Okay, sulfate is the negatively charged part of that compound. Here it is, soluble with most things, but not with any of these. But I don't see sodium in that list, so this is soluble. All right, does that make sense on how that works? Okay, top row soluble, bottom row insoluble. Pretty simple. All right, now we're going to talk about water and the polar molecule stuff here. Okay, so earlier in the unit we talked about how atoms of different elements can form compounds. Electrons are gained and lost, and sometimes electrons are shared. Okay, well, in water they're shared. Okay, hydrogen and oxygen share their electrons. Okay, so when we're looking at this here, okay, this electron actually belongs to hydrogen. Okay, but it's sharing it with oxygen. Okay, this electron actually belongs to hydrogen, but it's sharing it with oxygen. And then we would probably also say that maybe this one here belongs to, this one here belongs to oxygen, but it's sharing it sort of with hydrogen. This one belongs to oxygen, but it's sort of sharing it with this hydrogen here. Okay, why do I say sort of sharing? It can go both ways between them, but it's not an equal sharing. Okay, we say sharing like it's, you know, oh, there's one last pizza, we'll cut it exactly in half and we'll each have half of it. Well, oxygen isn't like that. Oxygen is that person who sees the last piece of pizza and reaches for it before anyone else can get it. Okay? Oxygen is very what we call electronegative. Okay? There are many elements that are very electronegative, which means they are highly attracted to or can very tightly hold on to electrons. Okay. Now, oxygen's got an electronegativity of, and I don't know if it's on your periodic table or not. It's not on this one. It is on yours. Okay? So oxygen, the electronegativity is right underneath the atomic number. All right? So for oxygen, you see the atomic number is 8, and right underneath there you see a 3.4. All right? That's oxygen's electronegativity, 3.4. For hydrogen, that number is 2.2. Who can hold the electrons harder? Oxygen or hydrogen? Oxygen's electronegativity is bigger. So what happens is, while hydrogen is sharing its electron, oxygen is not so much. And so what happens is, the electrons from hydrogen end up spending more time down here than they do up here. And as a result, we get a negatively charged side of the compound or molecule, and we get a positively charged side of the molecule. Okay? Because essentially what this is it's shaped like a Mickey Mouse. Okay? You know, like the little hats you can get at Disneyland. Okay? The ears are protons. Okay? Because that's what hydrogen is. It's one proton and one electron, and if the electrons are constantly being held down in this area, it's like there's two positive charges sticking out the top of the molecule. All right? They're bare, they're exposed. There's no electron ever traveling around that side, okay? So it appears very positive. Meanwhile, the bottom of the molecule, okay, looks very negative because the electrons are spending more time down in this area, okay, because oxygen holds on to them more often. All right? That creates a positive end and a negative end, or poles. Okay? Hence the name polar molecule. Okay? There is a positive end and a negative end. Okay? It's polarized or polar. Okay? Because it's got two different ends. Everyone follow me on that one? Yeah? Okay? You guys have heard of the term bipolar? Okay? It's actually a terrible thing to. It's actually an incorrect use of the word. Polar already means two. Okay? Putting bi on there doesn't make any sense. Polar is two. Okay? If you're polar, you go from one side to the other. I don't know how you can be two polar. Yeah, it's weird. Anyway, okay? So two nonmetals collide and react. Okay? They tend to share their electrons in a covalent bond. Okay? But that covalent bond doesn't mean the sharing is equal. All right? So we talked about this electronegativity thing. So covalent bonds in which electrons are unequally shared, okay, are called polar covalent bonds. So yes, they're sharing, but the electrons spend more time at one end of the molecule than the other. All right, now, you're probably thinking, so what? Okay, well, yeah, I can understand where you might get that. Here's the thing. Having a positive end and a negative end makes water able to do a lot of really strange things. Well, not so much strange. We're familiar with water doing them, okay? But they're strange in that only water really does them. All right? What happens when you freeze water? What does it do? It expands. What are most things supposed to do when they get cooler? Contract. Water does to a point, okay? Water takes up the least amount of volume at about 4 degrees Celsius. Okay? As you start to cool past 4 degrees Celsius, water begins to expand. All right? It begins to get bigger, and here's why. If you've got all these positive and negative ends, okay, and you start trying to force them closer together, you start getting positives close to positives. What will they do? Right. They'll repel. They'll push away from each other. Okay? And that happens right at the freezing point of water. It kind of gets to this kind of critical mass and then jumps. Okay? And forces away, and that's why if you fill a water bottle all the way to the top and throw it in the fridge, it will break. Okay? Or the bottom of it will expand outwards. You've probably seen that, right? If you accidentally froze your water bottle and you set it on the table, it falls over. Okay? Because the bottom pushes out. All right? The water expands inside of the bottle. Yeah? Okay? And you definitely don't want to do that with anything in a glass bottle, right? Because then you will have a horrid, horrid mess, okay, in your freezer later. All right. Okay. So we got our polar covalent bonds. There's a polar bond between hydrogen and oxygen here and here. Okay? So oxygen is slightly negative, the hydrogens are slightly positive. And then what they'll do is they'll bond to each other. Okay, so when water is a liquid, we often see that water does things that most other things as liquids don't. All right? You ever noticed you can fill a glass more than full? Slightly more than full? Right? Kind of makes that round kind of thing over the top. We call it a meniscus. Okay, goes over the top. Anyone ever seen that before? All right? Why? Why does that happen? You can't do that with other liquids. Surface tension. All right? Surface tension is caused by all these little bonds between the hydrogen of one water molecule and the oxygen of another. Okay? We call that hydrogen bonding. It's not really strong. Okay? It isn't really strong. You've probably noticed that. As soon as you touch the meniscus, usually that's when there floods over the sides. All right? And it's not because you put pressure on it. It's because you broke the hydrogen bonds. They're very weak. But they can go back really quickly. You can break them, but they'll reform really, really fast. Right? So as that water, if it's really cold, is going down the side of the glass, you ever notice how it kind of slows down as it goes down the side of the glass, and sometimes it'll actually just stick there? Okay? because the same thing is going on. Okay, the water is hydrogen bonding to the glass. Right? It's finding something that's positively or negatively charged and it's creating a hydrogen bond with it, okay? And that allows it to essentially defy gravity and stick to the side of the glass until, of course, it gets too big, okay? And then the hydrogen bonds aren't big enough or strong enough anymore and it runs down the side of the glass. Yes, yeah. If you wax a car, okay, or something like that, and the water hits it, it hits it in beads, right? And so the surface tension, the reason it beads is because the water hydrogen bonds with itself, and it can't penetrate the wax, and so it runs off the wax. Only because the wax is actually turning back into a solid. That's different. Yeah, okay, because wax melts as the candle burns, but as it runs down and gets away from the flame, it solidifies again. Right? So it's slowing down not because it's hydrogen bonding, but because it's turning back into a solid. Yeah. All right, so that's what we're looking at there. Hydrogen bonding, okay, allows for that surface tension, okay, and it allows plants to transport water from their roots to their leaves, okay. And for some plants, that's a long way. Right? If we're talking like a giant redwood or a sequoia or one of those big, huge trees, that's hundreds of feet. Okay, sometimes, well, let's use metric here. Some of those trees can be over 100 meters tall. All right, they actually have some in California, okay, where they actually cut holes in them and you drive through the tree. Okay, they're that big, they're that tall. So how do you get water from the roots over 100 meters up in the air? Okay, trees don't have pumps. Okay, there's not a pump in there going quick, 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 and squishing the water up the tree. Okay, it's using this hydrogen bonding. As water evaporates from the leaf, okay, all the water molecules that are inside the tubes, which are microscopically small, okay, inside the tree, are hydrogen bonded to each other. And you guys ever play with the barrel of monkeys? Right? I know it's like a cheesy toy, but you all have seen it, right? The barrel of monkeys with the hooked arms and legs. Okay, that's what it's like. As the tree is pulling water up, it's like all the water molecules are hooked together. When you pull on the top one, all the other ones come along with it. Okay, and it can pull all this water up the tree. Again, the tubes are microscopic. They have to be, because the water isn't just bonded to the water molecule above it, it's also hydrogen bonded to the inside of the tree. Right? And that keeps it from falling back down, as long as the tubes are small. If the tubes are big, it doesn't work. All right? Like, for example, there's essentially a finite size for a straw that can be effective. Okay? If you try and make a big straw, like let's say that big around, like let's say 4 centimeters, 5 centimeters in diameter, it would be very difficult for you to draw fluid up that straw. Okay? Because there's too much fluid in the middle of the straw that is unsupported, okay, by anything other than the suction that you can produce. And honestly, we can't produce that much suction. Okay? But if you have a really small straw, okay, you could make that straw really, really long because there isn't as much unsupported weight in the middle of the straw anymore. Okay? And you can actually draw water up a very small straw quite a bit further than you could a very big straw. All right? So if you've ever used a Slurpee straw, okay, they're quite a bit bigger than the little tiny ones. Okay? Now, obviously, with Slurpees, it's different because they're sort of semi-solid. You can use them in a big straw because they freeze together and they kind of support themselves in the middle. All right? But if you try that with just fluid, it's actually a little more difficult. All right, so polar covalent bonds, big thing we need to remember. Electrons are not equally shared.
Interruption. This time we're going to start our high school photo day.
Okay. Next thing, okay, water molecule is kind of like a right angle. Has to be, because you can't get those protons, those hydrogen atoms very close together because they repel each other, right? So there's a certain distance apart that they stay, okay? And again, they're the positive ends of the water molecule, okay? And there's actually kind of 2 negative sides, okay, to the bottom of the water molecule, okay, the oxygen atom there, right? And so one water molecule can bond to 4 others. All right, so 2 will attract protons to the bottom, okay, and the protons will attract oxygen atoms, okay, from 2 others to the top. All right, so they can create quite a network of bonds between water molecules, and this is kind of what you see in snowflakes. All right, you sort of see the evidence of this when water becomes crystalline or solid. Okay, and so those patterns can be quite random, and obviously no 2 snowflakes are alike. Okay. All right, so the big thing to remember here, okay, is that there is unequal sharing of electrons, okay, and that gives it a slightly positive end and a slightly negative end. Okay, questions on that? All right, so this is what, like, and we've already discussed all this stuff. This is what gives us the anomalous properties of water. Expansion when it freezes, okay? Here's what water looks like when it's at about 4 degrees Celsius. Okay, we can see that the water molecules are quite close together, right? But when water freezes, okay, you get this pushing away effect, okay, and the water actually expands when it becomes ice, right? Now, believe it or not, it's really important that water does that, because if it didn't, where would ice form? Right. Lakes would freeze from the bottom up. Because water does this, ice is less dense than its liquid counterpart, water. Okay? And so ice cubes float and lakes and stuff freeze from the top, not the bottom. Okay? It would be very, very different if water was like most things where their solids are more dense than their liquids. Okay? If you put a chunk of solid anything in its liquid counterpart, it sinks. Okay? Water's the exception to that rule. All right? It's actually less dense as a solid than it is as a liquid. Now, water can not just bond to itself, it can bond to other polar molecules like ammonia. All right? And so we can see that there's, you know, the nitrogen is negative, and so the hydrogen can bond to it. All right? And that's why water can actually hydrogen bond to other materials, okay, and stick to the sides of a glass or stick to wax on a car, okay, and stuff like that, because these things are also polar molecules, and these hydrogen bonds can form. Again, hydrogen bonds are not permanent. They're very weak, okay? But they break and reform very, very quickly. All right, so hydrogen bonds are formed between water molecules or between other kind of negatively charged or charged particles, okay? So attraction between polar molecules, that's the thing that causes that. All right, now, this is the explanation of how the tree, okay, I kind of explained this earlier, but this is how the tree, okay, pulls water up to the top. And we'll look at this again specifically when we talk about transport in plants in the Unit 2, okay? But you can see here that down at the roots, okay, water molecules move into the tubes called the xylem, okay, that transport water up a plant, okay? And inside those tubes, you can see that water bonds to itself, okay, and it also bonds to the inside of the xylem. So on the walls here, you can see here. Okay, this process here where it bonds to the wall is called adhesion. Okay, when it bonds to itself, it's called cohesion. All right, so cohesion here is water bonded to itself. All right, cohere, okay, or cooperate means to work together with people like you, okay, whereas adhere means to stick two things that are not alike together. All right, that's why glue is called an adhesive, okay? Usually you're sticking two things together that are not alike. All right, so big thing to remember here, okay, is that cohesion is between, okay, two water molecules, all right? So it contributes to the transport of water, so it's bonds between H2O particles. Okay, whereas adhesion is between H2O and something else. Questions on that? Okay, so adhesion, okay, is a clinging of one substance to another, so they're not alike. It's water to something else. Okay, you can see here is an example of surface tension or hydrogen bonding or cohesion, okay, of water. I have tried that time and time again. I spent like an hour and a half one day trying to make that happen, and I decided that was an hour and a half of my life I would never get back. Okay. Apparently you can do this, but I couldn't make it work. The key is you got to bend the pointy ends of the paper clip up. Otherwise, they will break the hydrogen bonds and the surface tension, and it will sink to the bottom. Okay. We talked about this, how on a freshly waxed car, you'll often see water beating up like this, but it's also true of plants. They have a waxy covering on the outside that prevents water from evaporating through their leaf tissue, which just helps them hold water in. Okay. It also means that any water that falls on their leaf will eventually run off the leaf, and land on the ground and be absorbed where their roots can get it. Okay, so it's all kind of very smart, evolutionarily speaking, okay, for them to do that. Okay, last thing, an animal that uses it. Okay, a couple of animals that use the hydrogen bonding of water, the cohesion. Okay, the Jesus lizard. Okay, you've probably seen him run across like little streams and little bodies of water. All right, essentially he moves fast enough, okay, and pushes lightly enough that he doesn't break the surface tension of the water, okay, and he can actually walk or run across the water. All right. Same thing with the water striders, the little bugs, okay, caddis flies. If you do any fly fishing, you rely on this quite a bit, actually, okay, to have your fly land on the water and stay on top of that surface tension, okay, without sinking. All right. It's easier, obviously, when the fly is dry or the fly is coated in oil, okay, or gel or something like that, okay. But as soon as the water starts to penetrate, it becomes much easier for it to sink down. Okay, so for these kind of flies that are real flies, not artificial ones, okay, they just spread their feet out, and they're light enough and their feet are structured properly that they don't break the surface tension. Unless some jerk comes along and drops a rock right next to them. Because then what happens? Yeah, the surface tension is broken, and those bonds don't reform very fast, and that bug will sink. All right, so something to think about. All right, questions on any of that? All good with that? Okay. All right, so that's it for today there, guys. We're going to start reactions tomorrow. All right, so we'll be moving right along here. We'll start reactions tomorrow, and then Thursday and Friday we're actually going to work on project.